All right. So, last time we left off on this, and I'm going to be honest, I don't really remember last time we were together that well because it's been a while, right? I'm sure that all of you are having the same issues. Did I tell you guys a story about formaldehyde poisoning and morticians? Okay, okay. And people thinking that their houses are haunted or they're possessed by demons? Okay, good. Good. If you're wondering what I'm talking about, then I guess check out the last video. We went into possession and people being possessed by demons and poltergeists in houses, right? How many of you were planning to have that on your bingo card for chemistry class, huh? All right. Now, this right here is another example of aldehyde. Benzaldehyde is this, see how that's really shiny? Yeah, that's benzaldehyde. Okay, it's the waxy substance that you typically would experience on like fruits like cherries. Okay, one of the reasons why a lot of people don't like cherries actually, they don't like the waxy substance on it, which is kind of interesting. Now, ketones. So probably the ketone you've experienced the most in your life is the butane and this is actually the flavoring of butter. And so that flavor of butter you're thinking of right now, that's butadiene. Okay. Now, that doesn't mean buttering flavor, the artificial stuff, is always made of this. It is typically a dione, but there's actually several compounds your tongue will experience and taste as butter. Okay. One of them was actually quite toxic, and they used to use it on artificial buttering flavors. They stopped using it, I think, sometime around like late 90s or something. So all of you, I don't think, have ever experienced it. But yeah, people actually died. So pyruvate is also an example of a ketone. This one being the like ubiquitous molecule in your body. Okay, as being on like you guys have heard of ketone bodies before, probably. Yeah, this one being what is usually produces most of the ketone bodies. It's a pretty ubiquitous compound in your um, biological systems. So aldehydes, ketones, extremely important for biological systems. Remember that ketones are going to have both sides where they have a carbon on it, and then aldehydes have one side where it's just hydrogen. Everybody sees that okay? Okay. So now this is a aldehyde because it has one side that has a hydrogen. This one just happens to have both sides having hydrogen. It doesn't have to. They can have one side being some sort of carbon. Okay. Okay. Everybody knows when I'm this picture right here for formaldehyde, that's not your brain. In fact, your brain should not have formaldehyde. Okay. It is actually the preservative that brain is in, and it's preserving that and keeping it from rotting. Okay. Okay. Now, monosaccharides, these are going to contain aldehyde functional group. It'll be called an aldose. If it contains a ketone, that's going to be a ketose. Okay. And notice the ose tells you that it's just sugar, doesn't it? That's the saccharide. And then the aldose, aldehyde, right? Ketose for ketone. All right, now, if we have a 3-carbon monosaccharide, that's going to be a triose. Tri is in 3, right? Ose is in saccharide. Okay. Tetrose is going to be 4 carbons. 5 carbons is going to be pentose. And 6 carbons, of course, is hexose, right? And so you can have a hexose, which is also an aldehyde, right? In which case you'd have an aldohexose. If you have, for example, a pentose that is a ketone, see that ketone group right there? Then that's going to be a ketopentose. Okay, and you can combine those terms together. Right. Now, this right here is what's called a Fischer projection. It's a very unique way of writing these out so that we know their stereochemistry very quickly. Okay. What you'll notice here is that you could have different sides. Anybody notice something about that carbon there? How many different groups does it have around it? So this side's different than this one, right? This side's different from that one. And so that has 4 different sides, doesn't it? If a carbon has 4 different sides, is it special in some way? It is, isn't it? It's a chiral carbon, right? So we have chiral carbon right there, don't we? How about that one? Also a chiral carbon, isn't it? This one? Also a chiral carbon, yeah. Yeah, they're all are, aren't they? How about that one? Nope, not a chiral carbon. Notice how it's not nicely drawn out so you can tell the different sides to it, is it? That's because it's not chiral, okay? You'll see the same thing over here. Anytime that we have a chiral carbon on these Fischer projections, we'll draw them out nicely so they have a little cross around them, right? And that's so you can tell what the enantiomer is right off the bat, okay? This is not how sugars exist in your blood at all, right? They do not like form these stretched out two-dimensional cross structures like that. That has nothing to do with how they actually look, okay? Is formatting so that you can easily tell what an enantiomer is. Okay, and so again, carbon atoms have tetrahedral geometry. When they have 4 different atoms or groups attached, they're going to be chiral centers, right? And that's that definition of chiral centers again. Compound with single chiral center can exist as 2 enantiomers. If it has more than 1 chiral center, you can have more enantiomers, can't you? Okay. So let's look at this one real quick. Again, we already talked about this, and I had you guys do this. This is chiral, isn't it? This down here is chiral, isn't it? This one here, not chiral. Yeah. All these ones here, they're chiral. This one has 2 hydrogens on it, doesn't it? So automatically that makes it achiral, not chiral, right? Okay. And so glucose here, this is glucose. This is in the glucose glycemic index. Glucose is in the glucose in your blood. Glucose is in the glucose that gets used by your brain. Only power source your brain uses. Those are this glucose right here. Okay. So this is one of the forms of glucose. Now, what you're going to see here is that we can actually have 2 different forms of every chiral center, can't we? One where the OH is on this side, but we could have also had it where it's flipped, right? That would be a different chirality. So let's go ahead and look at where we flipped one of these groups, okay? So here we have this portion right here, right? Everybody good with that so far? And notice this is similar to this. And this one here is going to be different here, isn't it? Everybody say okay? So we can have different orientations for these chiral centers. And if we flip certain chiral centers, we're going to actually have different sugars. Okay? Those will actually be different monosaccharides. Now, the number of stereoisomers possible is going to increase with your number of chiral centers present in a molecule. And so for molecules with 1 chiral center, you only have 2 possible stereoisomers. If you have more than 1 chiral center, you're going to have whatever that number is, 2 to the power of that number. Okay? So notice if we have 1 chiral center, that's 2 to the first power, and that's 2, isn't it? So we have the 2 chiral center enantiomers, which is the RS we were talking about a little bit. If we have 2 chiral centers, that would be 2 to the second power. Does everybody remember how you use powers? That's how many times you multiply them, right? So in that case, that would be 2 times 2, right? Which is 4. Okay. Now, glucose has 4 chiral centers, so that's going to be 2 times 2 times 2 times 2, isn't it? Okay. And so that's 2, 4, 8, 16, isn't it? So it has 16 possible stereoisomers that can exist from those 4 chiral centers. You can go through and just flip each of the OHs, and then you can flip 2 of them, and then you can flip 3 of them, and then you can flip 4 of them, and then you can flip all of them, right? Yeah. And so you can flip and get 16 possible stereoisomers. Now, what you'll notice is as you go through those, some of them are going to be complete mirror images to each other, aren't they? So if we were to flip all of the groups on one of the glucose, it's going to be a mirror image of each other that's non-superimposable, isn't it? Okay. Okay. And so only one of these stereoisomers is actually our preferred energy source. That is the glucose I was talking about before. The rest are going to actually have different names because they're going to be used differently, right? And so, for example, if you have glucose and you don't have any of the other sugars, your brain won't actually use those other sugars. Your brain does not actually use fructose, for example, okay? Not directly. It does not use the other stereoisomers. And so what happens is your body actually has to convert those stereoisomers to the proper one, which is the glucose. Okay. Now, I need to, before we go on any further, so that we can actually talk about these structures, we need to talk a bit about Fisher projections. That's what we were looking at before. That's called a Fisher projection, okay? It's a way of writing these out so you can see multiple stereocenters, multiple chiral centers that are laid out nicely so you can tell which one it is, okay? Now, in Fisher projections, your horizontal lines on the chiral center are going to always represent wedges. Remember, wedges are the ones that come out towards you, right? And then the vertical lines on the chiral centers are always going to represent dashes. And so those are going to be going out away from you, okay? So it looks like this every time you look at it. And basically what we have here is we have different hydrogens that are poking out and OHs that are poking out like this as we go around sort of like this. Is that making sense? Okay, so typically on a Fisher projection, we don't show the carbon. I know I showed it in the previous one, but that's not normal. Normally, we don't write out the carbons. We just let the line crossing tell you that's where our carbon is. Just like when we did our normal line edge, drawing out these things, same thing, okay? So where you have lines crossing, that's going to be where our carbon is. Now, it makes it a lot faster to draw out and a lot faster to read as well, okay? Now, when we're designating these, you're going to designate them with a D and L. This is going to be based on your Fisher projection positioning and your glyceraldehyde, and it's going to use a reference molecule for this designation. So what happened is they had glyceraldehyde. It's the simplest sugar, and so they drew that out in a Fisher projection, and then that stereochemistry dictated if it looks like that, it's D. If it looks like the other way, it's L. Okay? And they did that to make life really easy. But one of the things that happened when they did that is that the RS designations, the other designations, they actually don't make sense for any of the other sugars. And you're going to see in a little bit what I'm talking about. But understand that D and L only really have a physical meaning for glyceraldehyde, okay? All the other ones, it's literally just saying one chirality versus the other, okay? One enantiomer versus the other. Does that make sense? It really doesn't tell you anything about it. And so if you start looking into this more, you're going to get really confused, okay? Because the DNL designation is actually supposed to be how it turns light. You know how polarized lenses work at all? Like sunglasses? Not at all? Okay. So light can go different directions. A lot of the light that's around you bounces off objects and is going like this at you. Okay? And so when you wear sunglasses, it only allows the light that's going like this at you. And that's the one that lets through. And so all the stuff that are reflections off surfaces, it kind of dampens those down and makes those less. Okay? And that's if you get the nice polarized sunglasses. Anybody ever had those? Yeah. If you get the cheap pieces of junk that are tinted lenses, then no, won't do that, okay? If you want to know which one you have, you just take your sunglasses, put it in front of your computer screen, and just rotate it. If it goes dark at certain angles, then it's polarized. If it doesn't go dark from your computer screen, your cell phone screens, at certain angles, it's just tinted. It's not polarized. Okay. So, anyways, I'm not going to go super far into it, but understand if you try to look into this more for this DL designation, it's purely based on glyceraldehyde. It doesn't have any real meaning in terms of like physical structure or which one is going to be the one your body uses for all these, and it just doesn't have any meaning for all this. Okay, it's purely just I have this enantiomer. Okay, and that's an artifact of them making it easier for you to like just assign them based on the structures here, right? They've made it easy to identify when you're looking at it. In turn, they made it kind of useless for actually telling you anything about it. Okay. Now, this right here is the DNL glyceraldehydes. Okay, this is the one that you're based on. And so this is a wedge dash formatting that's in the same sort of orientation. See that? We've drawn it out so it looks very similar. Okay. And so again, as we go across horizontally, those are going to be your wedges coming out towards you, right? And so those are poking out towards you. Okay. As we look at the dashes, those are going away from you. Okay. And so they're going to be facing out away from you. Now, this is a Fischer projection. Again, this means the exact same thing, right? So this one that's horizontal here, the hydrogen is doing what? Poking out towards you, right? This OH here, going out towards you. Okay. Okay. This right here, this is achiral. It doesn't have chirality for that carbon, right? So you don't do anything special with that. You just write it out like a normal formula. So you don't care. This one, again, no chirality. So we just flat, doesn't have any chirality to it. Okay. This one here, that's chiral. Okay. Now, what you're seeing here is, notice on the left side, you have the OH, right? And so that's L. On this one over here, you have it on the right side. And so that's D. Okay. And so what you're going to see is you're going to look at the aldehyde or ketone. In this case, we have an aldehyde. You're going to go down the Fischer projection. The last chiral center, if a OH is on the right, that's a D. If the OH is on the left, that's an L. It makes it really easy to figure out. Also makes it, other than this one, it actually is what it's supposed to be. That's level rotary. It is what it's supposed to be. Meaning left-handed and German. Because they were the ones that were big chemistry, did a lot of research in chemistry at the time when this was a thing. By the way, an interesting little factoid about history is that this is actually the origins of Blitzkrieg, the mastering this chirality. And so they could get very, very pure drugs. And one of the drugs that they purified was meth. And the German soldiers would pop meth pills and be able to storm locations for 3 days behind tanks. And that's the origin of the Blitzkrieg. So it's also one of the reasons why they're like the villains of all time. Because you had an entire army of fucking meth addicts that conquered everybody around them and then tried to rule for a little while. As you can imagine, stuff got crazy. You ever been to New York or LA, then you know stuff gets crazy when you have a bunch of meth addicts roaming around. Imagine if all of them were armed and had tanks. Good God. The terror, huh? All right. This is what it looks like with a 3-dimensional model, by the way, in case anybody was trying to connect those in your heads. Okay, so this is, again, that stereochemistry we were just talking about. Again, that's just that, see, that's the L, this chiral center. They're mirror images of each other. They're non-superimposable. And that means they are enantiomers of each other, right? And so we found our enantiomers of each other right there. Okay? That only has the one chiral center, and so you don't have any other ones. Now, in this case, we're going to have more than one chiral center. And so again, that D sugars, that last chiral center one, the one furthest from the carbonyl, that is going to be on the right side of your molecule, okay? The enantiomer, the L sugar, is always going to be that OH on the left side. That's the furthest away from the carbonyl, okay? So that furthest chiral center from the carbonyl is going to have the OH on the left side. Now, most of the carbohydrates found in nature and the ones we use for energy are in fact D sugars. This is happening because this right here is a portion of that structure that gets reacted whenever we're looking at using sugars. So the majority of sugars found in nature are in fact D sugars. So this right here is going to be your enantiomers. So we're going to write them as if they're a mirror was placed between the two molecules. And so if you're given a D-glucose, how would you go ahead and figure out the L-glucose? Well, you would start with just copying this part right here, right? The up and down portion. Because it's going to be the same, isn't it? And then what you're going to do is you're going to act like you put a mirror here, right? And then all of these groups along here, they're going to get flipped. So you copy everything else but the OH and H's along here and here. And then every single one of those just flip. Okay? And that's all you got to do. It's actually pretty simple when you actually go to do it. Okay? Okay, now, we've talked about flipping them all. But what happens if you only flip like one or two of them? Okay? Well, that's where these other sugars that you've heard of before come into effect. And so, for example, right here we have galactose. Okay, that's going to be where we have not all of the chiral centers flipped from glucose. Okay, so let's quickly go through the steps of drawing out the enantiomer so that we can finish that up and go on to the next, where we'll see multiple examples of these different stereoisomers of our glucose, if you will. Okay, now, you're going to locate your chiral centers. That's these ones here, right? Again, if you have a Fisher projection, really easy. Yeah. They're the place where the lines cross, right? Yeah, I know. Yeah. Chemists are not super imaginative, but we do make like the easiest things to look at. Yeah. You don't have to memorize a lot of people's names either. And so this is D-galactose. If you're writing out the L-galactose, you're just going to switch all the horizontal groups on there, and that will give you the L-galactose. And that's it. Now, let's talk about stereoisomers. These are not going to be enantiomers because they are not mirror images of each other that cannot be superimposed. They are where you flipped one or more of the chiral centers. But because you haven't flipped all the chiral centers, they won't be mirror images. Okay? It'd be like if I was missing a finger or something, I wouldn't quite have a mirror image, right? And so I'm going to have a slightly different version. Okay? I'm going to have my stereoisomer, right? And so these are called diisomers, by the way, when you're talking about them. They're going to be stereoisomers that are not enantiomers. So diisomers. Again, they're going to be stereoisomers. They're not going to be exact mirror images of each other, and so they are not the D and L enantiomers of each other. They're going to be having different names. For example, here we have glucose, and we have that nicely color-coded so you can see that easier. And so if you compare that to galactose, you'll see this blue one is the one that's flipped, isn't it? Okay, see that? And so we flip this one right here. Okay, if we look at telos on the other hand, what we can see here is that versus, for example, the glucose here, this one's flipped and this one's flipped. Both of those are flipped. Okay? And so you don't have all of them flipped, you just have one or more of them flipped. Okay? As long as it's not all, you're not going to be an enantiomer. Right? As long as you have one of them flipped or more, you're going to be a diisomer. Okay, so we had talked about that we have 16 possible arrangements, possible stereoisomers for this, right? Because you can do two sides, and then there's 5 different places this can happen, right? And so I have drawn out all 16 of these for you. Is there 16 up there? Okay. What do you notice about the names of all these? Can you see that first letter? Is that D? No L's up there, is there? Yeah, I've drawn out all 16 because all you need to do for the other 8 is mirror image. So take a mirror, look at it, and you'll have the other 8, okay? And that's it. So whenever you draw these out, you only ever draw out the D's typically, and then you would just flip everything for the L's. Okay. You'll notice that the diisomers have different sugar names. You may have heard of mannose before. There's glucose. This is allose, altrose right there. You've probably heard of a lot of these, but not as just the base sugar, actually. Typically, you hear of them as like a derivative of that sugar, something like added to it that makes it indigestible, usually. So it's an artificial one. Anyways, this is D-glyceraldehyde. There's only one of them right, because the only thing you have for that is an L, an enantiomer, don't you? And then right here, you have 2 sites, 2 chiral centers, and so you have 2 of the D's. There'd be 2 L's, wouldn't there be? Okay. And then so on. Everybody okay with that? Okay. All right, so this is going to be glucose. This is the most abundant monosaccharide found in nature. It's also called dextrose or blood sugar oftentimes. It's found in fruits, vegetables, corn syrups, sodas, has a lot of glucose in it. Glucose can be broken down inside cells. This is going to produce energy through a process that's called glycolysis. Notice the glyco as in glucose, right? And lysis as in breaking, right? And so literally we're saying breaking down glucose. Okay? Now, diabetics actually have difficulty getting glucose from their bloodstream into their cells, and this is going to make it so it's difficult to have glycolysis occur. This is also why they have to regularly monitor their blood glucose levels, because they can literally starve to death and have their brain shut down. And despite the fact of having plenty of glucose in their blood and blood glucose everywhere, right? Very, very high. Glucose is also a sugar unit that's found in sucrose, which is table sugar. And so sucrose is a disaccharide that's composed of a glucose unit. Okay, and so it has a glucose in it. Lactose, which is milk sugar, amylose, amylopectin, glycogen, cellulose. Does everybody remember glycogen? It's basically the starch that exists in like animals. If everybody's ever seen like or touched a hard beer belly, it's what your beer belly would be made of. That's why it's harder and it's not like the fat, right? You have a little bit of glycogen as surroundings of your muscles and in your liver area. And so that's actually what you're feeling there. It's not fat, and you'll notice there's like a difference to it, right? It doesn't feel the same as the fat stores in your body. Okay? And so that's glycogen. Cellulose is in like my clothing right here. Cotton, cellulose, right? Okay, so galactose. This is going to be found combined with glucose. It's actually what compose these two together, give you the disaccharide lactose. That's the one in milk and dairy products, as in like lactose intolerant. Galactose has a single chiral center, carbon 4, that's arranged opposite of glucose. So it's only different on carbon 4. The diisomers that differ in just one chiral center, these are called epimers of each other. So these would be epimers of each other. So galactose and glucose are actually epimers of each other. So your body actually has an enzyme that we call epimerase that converts one into the other for these. So it actually converts galactose into the glucose. And that's the enzyme does it. You can guess why it's called epimerase, right? Because it transforms one epimer into the other, right? Yeah. Mannose. So mannose is actually kind of an interesting monosaccharide. Probably the most notable places it's found is in cranberries. It's actually not absorbed easily by the body. And so this is why, despite tasting fairly sweet and having a lot of sugar content in them, cranberries doesn't raise your blood sugar as much as like most other fruits, is because it would have mannose in it. And so you don't digest mannose very well. Cranberry juice has been largely promoted for treatment of things like urinary tract infections. This is thought to be because of the excess mannose being flushed through your urinary tract. To be honest, though, there isn't a lot of really strong evidence for this, and there's evidence that maybe it's not that helpful. So, I know people that swear by it, though, so I don't know. It just doesn't have really strong evidence right now, one way or the other, really. So, don't know. Somebody can do a study someday, like a large scale study for me. Send it to me and tell me, Dr. Clausen, cranberry juice is the way, or Dr. Clausen, cranberry juice is not. Now, it could partially be the acidity of your urine would change that as well. Yeah. So, fructose. Everybody knows fructose really well in the United States, of course. High fructose corn syrup exists. Now, the ketose is a ketose. It's referred to as the fruit sugar or levulose. It's actually found in fruits, vegetables. It's found in honey to some degree. Also found in, of course, corn. Okay. In combination with glucose, it actually gives the disaccharide sucrose, which is table sugar. Everybody's heard the Mexican Coke cane sugar thing? Okay. Do you know what the difference between Mexican Coke that's been on the store shelf for 2 weeks and American Coke is? Nothing. There is no difference. Yeah. They have almost the exact same sugar profile. You maybe, if you're sensitive enough, can taste the very tiny difference of about 5% difference concentration. But that's it. Okay? And the reason for that is Coca-Cola is acidic. And so what happens is in acidic environments, when you have a disaccharide, it actually breaks down to its monosaccharides, meaning that when you're talking about Coca-Cola sitting on a shelf doing its reaction for weeks on end, it split up the sucrose that they paid all that money for into glucose and fructose. And so you get glucose and fructose as well. Now, admittedly, when it's freshly bottled, it does actually still have sucrose in it. And so if you get freshly bottled one, it would be sucrose you're tasting. I don't think there's actually that much of a difference in taste, though, if you actually were to sit there and taste glucose, sucrose, and fructose. And I have a funny feeling most people won't be able to tell the difference. If you've ever taste tested it too, though, you can actually tell the difference, because there's a trace sugar that gets involved in there that has nothing to do with any of that. So there's a trace sugar that it's not because of the cane sugar that you probably can tell the difference. But again, that's a food study thing. That's psychological to some degree. All right, so fructose is actually the sweetest monosaccharide. It's 1.5 times sweeter than table sugar. And so oftentimes they use fructose, not because they're cheaping out necessarily, or they're trying to like make you unhealthy or something. It's because it is actually sweeter per gram, so they don't have to add as much of it. Okay? And so they can actually get away with lowering the sugar content for a sweeter drink. Okay? Now, it is not an epimer of glucose, so fructose can be broken down for energy production in the body, even though it's not an epimer of glucose. It's still a very, very common sugar in fruits, and so our body has adapted methods to convert that so it can be broken down. Ribose. So you may recognize ribose as in ribonucleic acid, right? As in RNA. Okay? And so this is part of the backbone of RNA. It is a 5-carbon sugar instead of a 6-carbon, like we were talking about before. Now, if you remove the oxygen from this second position right here, that's going to give you deoxyribose, or 2-deoxyribose, full name. And that is where the name for DNA comes from. That is deoxyribonucleic acid. Okay? And so it's missing that OH right there. Now, structurally, the only difference between two pentoses is going to be the absence of the oxygen, and that's that carbon 2 position. Ribose is also found in vitamin riboflavin. That's where the ribo in that name comes from as well. It is one of the more important biological compounds in terms of your molecules being made. Of course, your DNA being involved in it, your ATP being involved, that should tell you a lot. It's very, very important. Now, let's talk a bit more about diabetes. So glucose levels in the blood and cells are going to be strictly regulated typically by signaling hormones. When blood glucose levels rise after a meal, the hormone insulin signals tell your cells to take up the glucose. This glucose should either be broken down for energy or stored as glycogen, essentially, for the most part. It can actually be further stored into fats eventually if you needed, but yeah. Now, during periods of fasting, sleep, where you're not eating, what your body should do is it should have a hormone that's called glucagon. That's going to signal your liver primarily to make glucose. This is going to increase your blood sugar levels, and so you should stay, fairly regulated. You do bob around quite a bit, but you should stay somewhere between like 80 and 120 for your blood glucose levels. Unfortunately, this does not work perfectly in people, and so this number is way higher now, by the way. 10% is really low, and that's because this book's like 10 years old now. Unfortunately, this is a huge amount of the U.S. population has diabetes, and this is a chronic disease. They have not, well, actually, there are two things that may be cures for it, but they're very expensive, and they haven't really tested them that much yet. So there are some cures that might be coming, which is pretty cool. But so diabetes is going to be characterized by prolonged periods of high blood sugar. You can actually have, there's different types of diabetes. And so you can actually have, there's actually quite a few different types of diabetes if you get into it. And you can have ones that people will be low on blood sugar as well. But the most common is high on blood sugar. And so cells do not take up glucose. Type 1 diabetes, the insulin production is low. And so supplemental insulin is required, and that's the one where you see people taking insulin. Or there's a few other drugs they can use to kind of get around having to take insulin. But in type 2 diabetes, the insulin signal is just not received. And so your cells just don't receive insulin, either because they built up a resistance against receiving it, or they don't have some portion of that pathway. And so 95% of cases of diabetes are actually this type. This can often be controlled using diet, exercise, weight loss, and medications. And so you have a less active response to the insulin that you would be excreting, or no response at all. Okay. So that's diabetes. Anybody know what our leading cost, our single largest item on the United States budget is every year? Diabetes. Yeah. So all the different forms of diabetes treatment. That is actually our single largest line item on the United States budget every year now. So it's been that way for about 6 years now. It crossed over. Yeah. So big deal. In case you're wondering. Interesting little factoid. I didn't know this until I looked it up recently. Did you know we spend on our public medical systems $7,000 per citizen in this country? We actually spend the exact same amount as Sweden. I didn't know that. That's actually kind of interesting. Okay, so the linear structures, these are not going to show how most monosaccharides are actually structured in your bloodstream. They look very different than that. They are not like linear structures that are poking out like that. So pentose and hexoses, these are 5 and 6 carbon monosaccharides. They're going to bend back onto themselves, and what they're going to do is they're actually going to form rings. Because remember, the most stable rings are going to be 5 and 6 membered rings, right? And so they're very stable as rings. So when the opposite charges on different functional groups within the monosaccharides is tracked strongly enough, the new bonds are going to be formed and other bonds are going to be broken, and this is going to form you into a ring structure. And so the carbonyl group that's present on your aldehyde ketones, this is very polar, it's a very reactive group, and so it tends to form reactions in your blood. And so you have the partially positive carbon on that carbonyl right here. This is going to be attracted to that negative oxygen that's on the other side of that ring. So you have that sugar, right? You had the carbonyl on one side, and then you had an OH on the other. And so because it's long enough, it can wrap back around, and these can start coming near each other. Okay? They're going to be attracted to each other because you have a partial positive charge here, negative charge right there. And so these are going to start forming a bond. It's going to pull these electrons over. And what's going to happen is you're going to make a bond. This is called a hemiacetal product right here. And you'll notice that essentially what you get is you get an ether here, right? See that? And then you get an OH on that, what used to be your carbonyl. Okay? And so this is hemiacetal product. Now, this is the acetyl. Hemi means half. So we have half of it as an acetyl. Okay? Okay, so this is what that looks like. This right here is called the anomeric carbon. It's the one with the carbonyl. Okay? This is the Fischer projection of it. And what we're going to see is this is going to wrap back around. See this blue one here? This is going to wrap back around and react with that carbon. All right? And so this would be that reaction happening that we just looked at. And so it's wrapping around, and you get this oxygen coming near that carbon right there, and it's going to react. This is going to give you your hemiacetal. Now, this is called anomeric because it actually creates two anomers, is what those are called. Okay? They're going to be another form of stereoisomer. All right? And so what you can get here is if I have this and it wraps around like this, I have above and below, don't I? Okay? But what if it comes around the other way? I'm going to have a very similar structure, but there's just a little bit of a difference, isn't there? See that? You're going to have just a tiny bit of a difference, and that's the anomeric, or the anomers of each other. Okay? And so what you're getting here is, see that carbonyl oxygen right there? Okay. This one ends up off the ring. Can you see that? That red oxygen? That's the carbonyl one. Okay. And so what we'll have is we'll have the alpha form, which is one anomer, and the beta form. Okay. They're pretty easy to tell the difference of. So what you have here is, see this one right here, that's that last 6 carbon here? Okay. So this group right here with the OH, the one that's on the opposite side from that, that's the alpha. The one that's on the same side as that, that's the beta. Okay. I always kind of remember it because alpha is down low, right? And so it's lower side. Beta is up higher for its center of mass, right? And so it's the above one. Okay. It's on the same side or the above side of the ring. Alpha, low side, down. Okay. Okay. And so this right here would be the alpha D-glucose. This one here would be the beta D-glucose. And there we have the two anomers of that glucose. Both of them are still D-glucose. They're just their ring structures are slightly different. Okay. Now, this is really going to matter when we get things like disaccharides and polysaccharides, because these groups are going to be what are used to bind things together. And so you're going to get different structures if you bind these things, right? Okay. All right, now, again, we have two structures that are possible. Those are the anomers of each other. These are two interconvertible forms. So what's going to happen is in your blood, these will actually open up and reform all the time. You'll have about 99% of the glucose in these forms here, and then about 1% in this form at any given time. Okay? And so literally what's happening in your blood is this opens up, straight chain for a little bit, closes, opens up, straight chain for a little bit, and close back the same way, or it can close the other way. Okay? And it's just going to do that all the time in your blood, constantly. Right? Okay. Now, if in any monosaccharide, the carbonyl carbon forms the hemiacetal, this is going to be known as the anomeric carbon when we're looking at that. The anomeric carbon is going to be the only one that carbon where it's bonded directly to two oxygens. So they're very easy to see whenever you have the anomeric forms, the ring forms here, because see, this one has two oxygens bonded to it. Right here. One. This one here has two oxygens bonded to it. There'll never be another oxygen carbon that's bonded to two oxygens in these. And so it's always the two oxygen bonded one. Now, the two hemiacetal anomers of D-glucose, those are going to be alpha and beta. They're going to have that same designation every time. Remember, it's always going to be the one that's on the opposite side is alpha. The one on the same side as that carbon with the OH that pops up is going to be the beta. Okay. Again, it's going to be the carbon outside the ring that you're looking for every time. There's only ever one carbon outside the ring that you have to deal with for those. Now, the six-membered ring form of the diisomers, these are going to be known as pyranose. And so that's actually the six-membered one. The C6, by designation, is always drawn on the top side of the ring. And so if you draw these properly, if they're drawn properly, then it's always going to be, well, the beta is up on the same side top right. And then the alpha is always on the opposite side, and so it'll be bottom. Okay? All right, so let's talk about drawing the rings here. So this right here is we're filling in this ring. And so we've drawn everything but the OHs and the hydrogens so far, because those are the parts that are different depending on the sugar we're talking about, right? Okay. And so this is the scaffolding of the ring right here. Now you would put the OH either in the alpha or beta as directed. So if you're drawing the alpha, that's going to be downwards, right? The OH is down here. Beta is up there. Okay. Once you have the alpha and beta, then you can line up all the other OHs on the proper sides. Okay. Now, for the C2, that's this one, C3 and C4, they're going to be on the right side of the Fisher projection that you saw in the previous Fisher projection. And so what's going to happen on those is we're going to place them, if they're on the right side, they're going to be on the bottom of the ring. If they're on the left side, they're going to be on the top of the ring. Okay? And so that's how you choose which is on the top and bottom. Okay? Did everybody get that okay? You're going to want to write that somewhere in your notes. Make sure you can find it later, because it's not super bolded in my power presentation. And sometimes it's a little hard to find. So right side of the Fisher projection, that's placed on the bottom. Left side is going to be on the Fisher projection, is going to be at the top of the ring. Okay, so let's talk about a ketone. So D-fructose, this contains a ketone instead of an aldehyde. And so it's going to have several hydroxyl groups as well. The OH on the carbon 5 can curl around and react with the carbonyl position on the carbon 2. This is going to give you 2 possible ring structures, very similar to what we were talking about before. 4 carbons and an oxygen, this is going to give you a 5-membered ring. And so that 5-membered ring with the oxygen in it is called furanose. Okay? And that's going to give you furanose. 2 of the carbons, C1 and C6, are actually going to remain outside the ring in this case. Because remember, in this case, we don't have it at the end of the ring for the oxygen. We have it one step further in, don't we? Okay. And so the alpha and beta anomers are going to be determined by the positioning of the OH group on the anomere carbon related to the carbon 6 outside the ring. And so alpha is going to, again, be trans on the opposite side of the C6. The beta is going to be on the same side as the C6, cis. Okay, so this is what I was talking about. So this one right here, this is a ketone, right? And so in this case, we're attacking this carbon. Now notice that leaves a carbon out here, doesn't it? Everybody see that okay? That we end up with, instead of having the carbonyl right here, it's over here, isn't it? Okay. So when we wrap back around, we get 2 things happening. We have one less carbon in the ring, and that carbon ends up on the outside of the ring, doesn't it? Okay. And so we're wrapping back around, same as before, just a little bit more slack outside the ring, right? And so we can go either direction. Those are going to be our alpha betas. Okay. And what we're going to see here is that it's going to bond back over. We're again going to get that OH here. But instead of carbon 1 being right here, where it's the anomere carbon, it's instead outside the ring. Okay? And so that's actually going to dictate what our alpha beta is. So our carbon 6 here, on the opposite side, that's our alpha. Okay. How do I know this isn't carbon 6? It's on the same carbon as the anomere carbon, right? See that? It's attached to the anomere carbon. So it can't be carbon 6. Okay. So this is carbon 6, opposite side, that's an alpha. This is carbon 6, it's on the same side now, and so that's the beta. Okay. And this again is the anomere carbon because it has how many oxygens attached to it? 2. It's the only one that has 2 oxygens attached to it, right? So that's always the anomere carbon. Okay. So let's talk a bit more about reactions with these monosaccharides. You remember your oxidation reductions here, right? Oxidations, we add more oxygens, right? Reductions, we remove oxygens or add hydrogens, don't we? Okay. Now, the carbonyl group in aldoses, this can undergo organic oxidation reduction. It's very common, actually. This is going to occur by adding oxygen or losing hydrogens during oxidations, or by adding hydrogens or losing oxygens during reductions. In monosaccharides, the oxygen produces sugar acid, and the production produces sugar alcohols. Anybody ever heard of sugar alcohol before? Guess what? That's this one. So one of the common tests that gets used for this a lot is what's called the Benedict's test. Okay, and this is actually used to test for the presence of aldose in solution. Anybody ever seen Sherlock Holmes in anything? Or read Sherlock Holmes, or know who Sherlock Holmes is? Okay. This is a test that was very, very popular back in the Sherlock Holmes days. Okay. And so this is how they test for sugars, reducible sugars. So Benedict's test tests for the presence of aldose in solution. Copper 2+ is soluble. It'll color the initial reaction, solution blue, and it's quite a distinct looking blue. An aldehyde group will undergo oxidation. This will reduce your copper ions from copper 2+ to copper 1+. This copper 1+ oxide, it forms this brick red precipitate in solution, and it's not very soluble. And so your solution goes from being a nice distinct blue, it'll go less and less blue, and what you'll get is a brick red precipitate oftentimes looks black in the blue solution at first, but later on, when you get it more of it, you'll see it's like very brick red. Okay. Now, the aldoses are going to be easily oxidized, and so they can serve as what's called reducing sugars. And again, these are going to be referred to as reducing sugars. Okay. And it's because they're so easily oxidized that they can reduce things. Fructose and other ketoses are also going to be reducing sugars, even though they do not contain an aldehyde group, because they can rearrange to aldoses in the presence of an oxidizing agent. They can act as reducing sugars. Now, all monosaccharides are going to be reducing sugars. And so it's a very simple test to be able to tell the difference between a disaccharide, polysaccharide versus a monosaccharide. Okay? And it's fairly simple to perform. This is, in general, what it kind of looks like. So you'll have the Benedict solution right here. And then what you're going to do is you'll put a little sample of the sugar you want to test or the substance you want to test. And you're like, is this a sugar? And then you'd put that in. And if it's a sugar, a monosaccharide, it's going to go ahead and reduce the copper. And this is going to give you like a brick red precipitate in there. Okay. Now, your book kind of makes it look weird because this is more red than I've ever seen these look. They must be either this is just a fake photograph or they have done something to greatly enhance that redness. Okay. It is not normally that red looking. Maybe they're passing through light or they've just done a heck of a lot of this reaction. Like this could be really thick. And then they've went and stirred it up a lot. It doesn't usually stay suspended. It falls out as a precipitate. So what you usually end up with is like a bunch of this like darker colored brick red solution down here. Like a brick down there, if you will. So aldoses or ketoses, this can be reduced to an alcohol when the carbonyl reacts with hydrogen. Sugar alcohols still taste sweet to you. They don't have calories that are found in monosaccharides because you've actually removed one of the spots you need to attack to digest them. Okay, so they're quite difficult for your body to digest. Some of the examples of this are things like sorbitol, xylitol, and erythritol. These are often added to things like sugar-free or low-calorie drinks and candies and stuff, which is where you've probably heard sugar alcohols before. The enzyme that's called aldose reductase, this actually acts to reduce excess glucose to the sugar alcohol sorbitol. And in very high concentrations, this sugar alcohol can contribute to cataracts. Though it's kind of arguable whether a normal person could ever reach those sort of concentrations. But I guess if you could just sit there eating candy all day. So yeah. Now, even when enclosed in a ring, an anomeric carbon is still reactive. Disaccharides are formed when two monosaccharides are joined through a condensation reaction. This is going to occur at the anomeric carbon, and that will give you your disaccharide, meaning two of these joined together. So we've talked about the monosaccharides before, now we're in the disaccharides. So, again, if you remember your condensation and hydrolysis, right? Condensation was forming the bonds, and we're removing a water, right? And then hydrolysis was putting a water across, breaking the bond, okay? And so these are going to be condensation forming what's called a glycosidic linkage or glycosidic bond. Hydrolysis is then going to be used to break a glycosidic bond, okay, which is glycosidic as in sugar, right? So this is the bond that joins together a disaccharide. Okay. Now, the monosaccharide ring form, the anomeric carbon has the most reactive OH in your molecule. And so in an aldose, this is going to be OC1. When the hydroxyl on the anomeric carbon reacts with the hydroxyl on another monosaccharide, you're going to form what's called a glycoside. Okay? As in like sugar, right? Glycoside. The bond that connects the two is going to be referred to as the glycosidic bond, as in it's the bond for the glycoside. And so the glycosidic bonds are going to join the monosaccharides to each other. This can connect the monosaccharides to any alcohol, so you can actually add a bunch of different things to these. You can make these monosaccharides where they have other compounds attached. As long as it's an alcohol, it's pretty easy to do. You can make disaccharides, you can make polysaccharides from this, etc. And that's why those all happen. So this right here is actually the formation of the disaccharide maltose. Everybody's had malt balls before? Yeah. Or tasted an actual malt with maltose in it? No? Oh, that's sad. It's like a very mild sweetness, and it has a very distinct flavor to it, right? Which is quite pleasant, actually, for most people. Yeah. Anyways, if you haven't had a chance, try it out. The malts are a little harder to find. The malt balls are pretty easy to find. Okay. Now, this is going to be two monosaccharides. This is the alpha-D-glucose reacting with another alpha-D-glucose. And so what we're going to get right here is we get a joining of them. This is a condensation reaction. See, we're losing water here. And we're making a glycosidic bond here. Now, notice that this one's an alpha. See that? Alpha anomer. And so this one down here, this is the alpha position glycosidic bond. Okay? And so it made an alpha position glycosidic bond. And this is going to be your disaccharide. It's going to be two D-glucose units, and it's going to be maltose. Or maltose, depending on how you would like to pronounce that. Now, the glycosidic bonds, again, depending on if it was the alpha or beta anomer that was performing that bond, we're going to have a bit of a different structure on it. And so we're going to have to specify, did we use the alpha or beta anomer? Okay. We also need to say, hey, which of the OHs did it connect to? Which carbon is it connected to? Okay. And so there's a lot of different hydroxyl groups that we could use to do these condensation bonds, right? Those things are everywhere on these sugars. And so we need to specify. Now, what the convention is to name the glycosidic bonds is we specify the anomeric form and the carbons that are bonded. So for maltose, we're going to have a glycosidic bond. It's going to be specified as alpha 1 to 4. Okay? I'm going to show you here in just a second. So this was the first one. See, that's that carbon 1, isn't it? That's the anomeric carbon. And it's in the alpha position because it's on the opposite side. And so that is alpha 1. And then it's going to, that's the fourth carbon. And so alpha 1, 4. If we had the beta, this is what that would look like. And so this is the beta, because it's on the same side, see? And that's beta 1, 4. Now, interestingly enough, this is maltose, as in like drinking malts. This right here is cellobiose, as in like making cellulose. Okay? So, surprisingly different, right? Yeah. Does anybody have any desire to drink a malt of this? I don't think it would necessarily taste awful, but it probably wouldn't taste very good. I think it would taste kind of like normal sugary drink, just not malty. Yeah. Never actually tried it though. I have avoided that. I know, sad. Now, there are three very important disaccharides that you probably want to know about. There's maltose, of course, as in like malt liquor, as in like malts, as in malt balls. There's lactose, and then there's sucrose. And so these are what those are. Maltose right here is two D-glucoses joined together, and then the glycosidic bond is an alpha 1, 4. When we're talking about lactose, this is a D-galactose and a D-glucose joined together through a condensation reaction. And this is going to be a glycosidic bond that's a beta 1, 4 in that case. These ones right here are going to be sucrose, and that's going to be D-glucose with D-fructose, and they form a glycosidic bond that's actually an alpha-beta 1,2. And interestingly enough, it's actually the anomeric carbon for both of these. So it's the anomeric carbons joined together for those two. And that's why it's alpha-beta. It's alpha on the first one, beta on the second. And that's where the 1,2 comes from. You may recognize this from the, this one has the second carbon involved in that, right? First carbon's up. But, yeah. I know things like are connecting a little bit, aren't they? Which is good. Now, again, maltose or malt sugar, disaccharide formed in the breakdown of starch typically. Malted barley has very high levels of maltose, which is why you get malt liquor, malted barley, maltose, as all those names. They're directly linked to each other. That's where the naming came from. Okay. So the glucose in the maltose of malted barley can be converted to alcohol by yeast. This is the process we know as fermentation, and that's how they get all the different malt liquors like beer and stuff. Okay. You know that the alcohol is actually their waste product. Okay. And so eventually they make so much of their waste product they kill themselves off. And then typically what people do is they then distill out the alcohol so they can build up the concentration of it. Okay. The yeast actually typically kills itself off at about 4% to 3% alcohol. Usually doesn't get anywhere near the 5% you'd see in most beers. So the glycosidic bond in maltose, again, is a alpha 1,4. And because one of the aromatic carbons is free, maltose is a reducing sugar. And so if you do a Benedict's test on this, it will show up as a reducing sugar. Okay. It's not as fast, though, in case you're curious. Like if you were to weigh out 1 gram of maltose versus 1 gram of glucose, glucose would be much faster. And so it would show you a much faster reduction. And you get that brick red going much faster. Okay. I will see you all next time. You all have a wonderful return day. Hopefully everybody's kicking butt, taking names, and doing great. Cool.